the next 30 minutes, we have Kyungjoo Noh, who was at Yale and now is at AWS Center for Quantum Computing. Today, talking about shifted Fock state basis method for analyzing large qubits. The talk will be 25 minutes plus 5 minutes for questions. And the floor is yours, Kyungjoo.
All right. Thanks a lot for the introduction, Stephen, and thanks a lot for organizing this amazing workshop again. So today I'm going to be talking about the shifted Fock basis method for analyzing large cat qubits. So this is a part of a large AWS project by these many people, and there's going to be another related talk on this Friday by our on more of a fault tolerant aspect of this cat code. But today I'm going to be mostly focusing on the physical part, on the cat qubit. So Liang already described, some basics about the two-component cat qubit, which is what we focus on here. So the cat qubit that we consider here is consisting of this plus minus alpha coherent states. And what this means is that if there is a mechanism that stabilizes this plus minus alpha coherent states, then it's really unlikely that there is a bit flip error. And the reason is basically because this plus minus alpha coherent states are far, very well separated in the phase space. So, if alpha is really, really large, it's very unlikely that, plus alpha is mapped to the minus alpha and vice versa. So in that sense, it's bit flip is really unlikely. But if we look at the complementary basis, the plus minus basis, then we have either even or odd cat states. So what that means is that if there is a single excitation loss, then this even cat state can be immediately mapped to the odd cat state, and the same thing goes the other way around too. So it's therefore quite likely that there may be some phase flip or Pauli Z errors. So this cat qubit naturally gives us a special qubit that has highly biased noise towards the phase split errors, and the ratio between this dominant Z error and non-Z errors are typically given by e to the minus 2 alpha squared, and that's going to be pretty important. So it turns out, I'm not going to be talking about in too much detail, but it turns out that to be able to do some useful applications and to really take advantage of this noise bias, it's likely that we need some large cat qubits. Here alpha square is the average excitation number, so we expect that we would need at least 6 or maybe even larger cat qubits, like with alpha square 8. So yeah, in any case, we really need some really big cat qubits. And in terms of then understanding and analyzing those cat qubits, there's this obvious challenge, which is that if we use the usual Fock basis, then it becomes really, really hard to simulate those large cat qubits. Especially, we want to simulate, say, important 2-qubit gate like the CNOT gate, and even 3-qubit gates like Toffoli gate, which turns out to be really important. So these are all important things, but because the cat qubits are too large, by using the usual Fock basis, it's not really easy to. It's not really possible to simulate, say, the 3-qubit Toffoli gate. So today I'm gonna introduce a tailored basis system that's really well suited to describe large cat qubits. So the usual Fock basis, just to recap, is consisting of, say, the vacuum state and the single photon state and 2 photon states and so on and so on and so on. So by using the usual Fock basis, and if we want to simulate some large cat qubits, we sometimes need 30-dimensional Hilbert space or even 50-dimensional Hilbert space. So the numerical simulation gets really quickly challenging. And what we propose to do here, this idea I think has been circulating in the field, but I'm trying to kind of formalize it in a little bit more detail. So the way we design the basis system is by starting with the logical states. And by logical states, I mean the plus minus alpha coherent states. And I'm basically representing that in terms of displaced vacuum state. if once we represent the plus minus alpha coherent states in this way, then it's really natural to extend the Hilbert space. And basically we add an excitation after or before the displacement. So we have this computational zero-like branch where we have plus alpha displaced vacuum state and plus alpha displaced single photon state and so on and so on. And we similarly build from minus alpha coherent state and define displaced or shifted Fock basis states. And this is in spirit really similar to this modular subsystem decomposition that turned out to be really useful for the GKP qubit. And in other words, what we are doing here is we have this infinite dimensional bosonic Hilbert space, and we basically have a subsystem decomposition, consisting of this qubit part, which describes the logical information, and this auxiliary oscillator part that describes the excitation from the desired cat-qubit manifold. And this turns out to be really useful for understanding and characterizing how the information is preserved and so on and so on. So to be able to work with this shifted Fock basis, it's really needed to understand how the annihilation operator is acting in this basis system. So it turns out that if we do the math, we can understand this annihilation operator in terms of like the Pauli Z error tensor with this auxiliary oscillator part of the operator. And this is in resonance with the earlier observation that single excitation loss immediately maps an even cat state to an odd cat state, and therefore induces a Pauli Z error. So this is consistent with that intuition. And also I should note that plus minus alpha coherent states are not exactly orthogonal to each other. So in practice, when we simulate the cat qubit, using the shifted Fock basis, we should really carefully take into account those non-orthogonality issues. But like in terms of like using the shifted Fock basis to have some conceptual understanding of the cat qubit, and especially if we only want to focus on getting the dominant Z error rates correctly, that's not really needed. So we ignore those exponentially small corrections, and we're going to be mostly working with this approximate expression for the purpose of this talk. So a immediate simple application of this is to apply this to understand what the single excitation loss is doing. And as can be seen from here, like we have this expression in the shifted Fock basis, and if we project this dissipator to the ground side of the cat-qubit manifold, then we end up getting this phase flip error with an effective phase flip error rate kappa 1 alpha squared, and we can immediately see that this bosonic enhancement factor comes into play. In other words, the higher the energy is, the more likely that we have this Pauli Z error. So again, like I should emphasize that with this approximate expression, we cannot capture the exponentially small non-Z error rates. But this is not a fundamental issue. It could be taken care of. So I'm gonna move on to another application of this shifted Fock basis, and with this shifted Fock basis, I'm gonna try to understand this engineered dissipator. So intuitively, what this engineered dissipator is doing is to stabilize this plus minus alpha coherent state. So in the usual Fock basis, that's kind of apparent, by noting that the plus minus alpha coherent states are annihilated by dissipator. So that kind of gives a sense that it does the right thing. But in the shifted Fock basis, it's even more apparent. So what's shown here is that if we express this jump operator in the shifted Fock basis, then we immediately see that this engineered dissipation brings the excited states manifold back to the code space. So if we look at the auxiliary part, we can understand whether the system is in the ground state manifold or in the first excited state manifold, and we can immediately see that this engineered dissipation brings back the excited states back to the code space. And also while doing that, because Pauli Z operator squares to identity, like we can see that this engineered dissipation does not distort the encoded logical information. And also, moreover, if we compute the engineered dissipation rate, I mean the effective dissipative gap, we immediately see that there's also this bosonic enhancement factor. So the actual dissipation rate, the physical dissipation rate is enhanced by this alpha square factor. And for those who are familiar with the work by the Zaki's group and this paper by Luskan and colleagues, this is related to what they called confinement rate. And there is a subtle difference about this factor too, but I'm just gonna skip that discussion. But those are perfectly consistent with each other. So with that, I'm gonna show a couple more applications of this shifted Fock basis in terms of like how it affects our parameter design for the hardware. So what's really important for implementing this cat qubit is to be able to engineer the two-photon dissipation. And the way we do it is by introducing a fast decaying ancillar, which decays with a really large decay rate kappa b, and then to engineer this Hamiltonian that basically exchanges a pair of photons from the A mode where the cat qubit is stored, and with the excitation in the B mode. So if we adiabatically eliminate the B mode, then we end up getting this engineered dissipation. And what's really important here is that for this adiabatic elimination to be valid, it's really important that the B mode stays in the ground state manifold, its ground state, and therefore the decay rate kappa b has to be much larger than G2. But then because we are thinking of some large cat qubits of like photon number 6 or 8 or even 10, it's quite important to also take into account the possible bosonic enhancement factor. And that bosonic enhancement factor really naturally manifests in the shifted Fock basis representation. So in the shifted Fock basis representation, this interaction can be understood as effective beam splitter interaction between this auxiliary mode and the B mode. And in this case, it's now more apparent that the correct adiabatic elimination condition has this factor alpha. So, and in practice, we find that the 1/5 or 0.2 is enough for this condition. But the important fact here is that there's this bosonic enhancement factor that we need to consider, and this is quite important. Like when we want to maximally take advantage of the decay rate here, and when we want to optimize everything, this is a really important factor to take into account, that there's this bosonic enhancement factor. So this was one application of the shifted Fock basis, and there's another also very interesting application, which is that, and this is not quite discussed in the literature, but this could be something very useful, especially when we want to have many cat qubits. So it's also possible that we consider using a single fast decaying ancillar to stabilize more than 2 cat qubits. And in that case, to have some incoherence, it's really important to have this detuning. So without the detuning, we have this coherent dissipator. So the stabilized manifold is much larger than we wanted to have. So to really have a desired incoherent dissipator, we should have some large enough detuning, and shifted Fock basis gives us this natural energy scale, and it tells us that this detuning has to be much larger than this twice the confinement rate, and also this bosonic enhancement factor can be of order 6 to 10. So when we design the parameters, taking into this account is really crucial. So so far I've been talking about the applications of the shifted Fock basis to the hardware design, and then I'm now gonna be move on to applications of the shifted Fock basis to simulate and understand various cat qubit gates. So just as a simplest example, I'm gonna be starting with this Z rotation, and this is something that was experimentally demonstrated by the Yale group, by Stephen and colleagues. So to implement a Z rotation, we need to have this engineered dissipation, and inevitably we are gonna have some excitation loss. And then to really induce the desired logical operation, we should add this linear drive. So we now understand like what this engineered dissipation is doing and what this single photon loss is doing in the shifted Fock basis. So now I'm gonna express this Hamiltonian in the shifted Fock basis. So if we use the shifted Fock basis, we then immediately can see that this Hamiltonian has the desired Z Hamiltonian part, and also it comes with this undesired term that actually excites the system out of the ground state manifold or the cat-cubic manifold. So and that's not a problem. I mean, that excitation is eventually gonna be brought back to the code space by this engineered dissipation. But like because there is this driven dissipative process, there is an additional Z error rate on the cat qubit, and by using another layer of adiabatic elimination, we can characterize those error rate, and we can then immediately see that there is this trade-off between doing the gate faster or slower. So on one hand, we want to do this gate faster because then we are going to suffer less from the single photon loss or single excitation loss. But if we want to do the gate faster, we should have a stronger Hamiltonian. And that means that it's more likely to have this undesired excitation from the code space. And therefore, this non-adiabatic error is going to be enhanced. So we have to balance these two different conflicting factors. And then once we balance this the gate time, then we end up realizing that the dominant Z error rate of the gate scales like root kappa 1 over kappa 2. And that's a little bit unfortunate in the sense that, you know, this kappa 1 over kappa 2 is kind of like a physical error rate. I mean, it's the ratio between the good dissipation versus the bad dissipation. So physically, I mean, right now, the state of the art, I believe, is kappa 1 over kappa 2 is 10 minus 2. And you know, we are thinking of engineering some system that has kappa 1 over kappa 2 of like 10 minus 4 or even maybe 10 minus 5. But what's really unfortunate is that it's been square rooted. So when it's translated into gate error rate, even if we have kappa 1 over kappa 2 10 minus 4, it translates to like 10 minus 2, so just a few percent of gate error rate. So that's a little bit unfortunate. But in this specific example, this bosonic enhancement factor is actually working in our favor. So that's at least the good news. But it's gonna turn out that this is not really the case for the CNOT and TOEFL gates. Yeah, but this is how you know, we could use the shifted Fock basis to have some, you know, nice understanding of how this gate is done and, you know, how these errors are generated. So with that, I'm going to move on to the CNOT gate, which is arguably more important. So to do this, when we think about doing the CNOT gate, what's really important is that, you know, we should make sure that the noise bias is preserved throughout the entire gate, and that's why, you know, we should think about this very specific way of doing the CNOT gate. So the key observation here is that to implement the CNOT gate, we have to implement a controlled bit flip on the target qubit. And bit flip here can be done by this 180-degree rotation. So what this means is that, you know, we have to be able to rotate the target node conditioned on the fact that the control is in computational 1 state or in minus alpha coherent state. So this very carefully designed engineered dissipation implements that, you know, that conditional rotation. But what's also important to realize here is that, you know, if we only rely on this dissipator, we should do this process really, really slowly to make sure that, you know, the system remains in the ground state manifold during this entire process. And for that reason, this gate could be pretty slow. And to compensate that non-adiabatic errors, we can also add this compensating Hamiltonian, which is essentially doing the same thing of rotating the target node only when the control is in the minus alpha coherent state. So just to have a little more understanding of how this works, I'm gonna again, you know, use the shifted Fock basis to analyze this this bias preserving CNOT gate. And also what's really important to point out is that because these two logical states are well separated in the phase space throughout the entire implementation of the gate, the noise is still biased towards the phase split error. And that's a really important design principle behind this scheme. So this is what we really want to have. I mean, this is the ideal compensating Hamiltonian that the target mode has to rotate only when the control is in one state. But in reality, this is almost impossible to realize in physical systems. So we should make a compromise and just have to work with this this cubic interaction. And because we made the compromise, this physically realizable Hamiltonian has this desired part. But on top of that, we also have this undesired term that turns out to excite the system out of the code space. And the key reason why that excitation happens is because the cat states are not an eigenstate of the excitation number operator. In other words, coherent states and cat states approximately follow Poissonian distribution. So even though the average excitation number is alpha squared, it's not always in that specific photon number, and there's going to be some photon number fluctuation. So this is going to have some non-trivial impact, and it's in particular going to give us an additional error on the Z1 control qubit. So it turns out that if we use the shifted Fock basis, this undesired effect can be understood as a joint excitation. And again, the engineered dissipation is going to bring back this excitation back to the code space. But while we do that, there's going to be some additional error associated with this adiabatic elimination. So like I said, this non-adiabatic error impacts the control, the Z1 part of the error rate only. But again, like we still have to make this balance between the incentive of doing things faster versus slower. And it again turns out that the optimal dominant Z error rates are scaling like root kappa 1 over kappa 2. And as I implied earlier, we don't have this alpha dependence anymore. So in some sense, it's a good news that 5 minutes. So in some sense that it's a good news that we can still increase alpha and have the same dominant Z error rates, but on the other hand, we still have to deal with this root kappa 1 over kappa 2 scaling. And another important thing is that this is just a perturbation theory, and it's basically saying that only a few excitations are enough to understand the C0 gate. So it turns out that indeed numerically, I mean, this was done mostly by Joe Iverson, that we can only use a finite dimensional Hilbert space if we use a shifted Fock basis, and that's enough to capture this dominant Z error rates, and the required Hilbert space dimension is independent of the size of the cat qubits, and that was why we could simulate this gate really efficiently. And the agreement between the perturbation theory and the exact numerics are pretty decent. And also, moreover, if we take into account the non-orthogonality very carefully when we use the shifted Fock basis, we can also resolve this exponentially small non-Z error rates. And we do indeed find that the noise bias vector is given by e to the minus 2 alpha squared. So that was nice. And I'll briefly talk about this very subtle point that dephasing can actually adversely impact the C0 gate. So what's typically said is that dephasing does not change the excitation number parity. So it's always believed that dephasing cannot do any damage to the cat qubit in terms of the dominant Z error rates. But it actually turns out that when we do this bias preserving C0 gate, because the target stabilization rotates non-trivially conditioned on the control qubit, it turns out that when the target stabilization brings back the excitation, there is some non-trivial Z error acted on the control qubit. So it's still true that dephasing doesn't change the excitation number parity, but dephasing still induces some heating. But then when that heated state comes back to the code space, there turns out to be some non-trivial Z error due to the dephasing, and that's mostly because of this engineered dissipation. So in some architecture, dephasing might really be a big issue, and it's really important to take into account that dephasing can really damage the dominant Z error rate for the cat qubit, which is kind of surprising. And also we can do some similar thing for the Toffoli gate, and we again the simulation of the Toffoli gate was out of reach in previous work by Jeremy and Margel. And in our case, thanks to the shifted Fock basis, we were able to simulate the dominant Z error rates of the bias preserving Toffoli gate by just using a constant dimensional Hilbert space. So with that, I'm gonna just briefly outline how the shifted Fock basis has been useful. So it's useful for understanding the relevant energy scale. It gives us the refined adiabatic elimination condition, and it also tells us how large the detuning has to be for us to have desired multiplex stabilization. We can have some pretty simple understanding of how the gates are performed and how the errors emerge. And we can also use this as an efficient numerical tool to understand these various important CNAT gates for cat qubit gates. So with that, I'll stop here, and I thank you for your attention.
Thank you, Kyungjoo. Great talk and quite amazing analysis of those stabilized cats. So I have two questions from the chat. So the first one, sorry. Sorry, the chat is a bit finicky to scroll. Yeah, so the first one is in your example with two cat modes, A1 and A2, you imagine that they are connected to the same B mode for dissipation. Why not one? So why not one B for every A? Why not one reservoir per mode?
That's right. So in terms of reducing crosstalk and for simplicity, for simplicity in analysis, it's better to have different ancillary modes for each different cat qubit. But this was mostly motivated by the need to reduce the hardware overhead. So we wanted to use as few ancillary mode possible. So we were considering like how much we could multiplex with this shared B mode. And also another important thing is that when we want to implement the bias preserving C0 gate, we have to engineer this non-trivial rotating dissipator. And this dissipator acts non-trivially both on A1 and A2. So it means that there has to be some physical element that's coupled to both A1 and A2. And that's another instance where we need some element that's coupled to both A1 and A2. So yeah, that was the key reasons why.
I see. So yeah, for the two mode gates. Can you elaborate on the nature of the tensor product decomposition? How does it relate to the virtual subsystem decomposition in Giacomo's paper recently put on the archive? I mean, last year put on the archive.
So, right. To me, so how that relates to this paper by this paper, right? So if that's the case, yeah, I mean, the way I see it is that this subsystem decomposition is a really general idea where, whenever we want to encode a qubit, it's ideal to have a decomposition like this so that we can just look at how logical information is distorted and how the gauge is being transformed. So that's a really general idea. So, and apart from, having the same philosophy, I will say that the details are different. I mean, this is just a tailored version of this decomposition for the cat qubit, and this previous work was simply tailored for the GKP qubits. So I would say it's the same general idea, but in the detailed implementation, it's different slightly.
Okay, there is a question about whether your numerical work is written somewhere. So I invite this question to be taken onto Slack, because like sharing resources and such might be more easily done there. So if the person who has the question would like to join Slack and maybe discuss directly with Kyungjoo. And Victor is asking if the shifted cat basis wouldn't be as nice to use while taking care of orthogonality issues better.
Sorry, what was the question again? Like,
if you could use a shifted cat
mm-hmm.
Basis instead of the shifted Fock basis.
Just take
So
plus and minus superpositions, right?
So I would say this includes shifted cat state, because I mean those are just basis states. So if we combine, you know, this and this shifted Fock state, you know, we get the shifted cat basis. Or maybe I don't understand what Victor's suggesting, but I was thinking that this
I assume the
includes
question
shifted.
is to group the shifted Fock states as into Fox shifted cats. Victor can take the.
Yeah, I mean it's just a change of basis, but that's, I mean, your shifted Fock basis is a change of basis as well. So I was curious, if you express it in this other basis, what changes?
Yeah, I'm still not quite sure what you have in mind, Victor. So maybe we can talk about this.
Yeah,
in
you
Slack
can.
or offline.
So if you take it offline, maybe Victor can make it clearer what he's thinking of. So if there is any other question that hasn't been asked in the chat, you can just unmute and ask. Otherwise, we'll go to our next speaker. All right, then let's thank Kyungjoo again, and let's go to our next speaker. So, Dmitry.